particular problem, we have water that flows through a horizontal pipe and then it goes out into the atmosphere with the speed V1 is 15 meters per second. And it gives us the diameter of the pipe. The wider section is 5 centimeters. The narrower section is 3 centimeters. So on the diagram here, this is V2 on the left. V1 is given to us 15 meters per second. All right, so there's inner, there's exit. All right, let's go ahead and crack out part A. Part A wants us to find the volume of water that flows into the atmosphere during a 10-minute period. So here is the entry water, and then there's the exit. V1 is given as 15 meters per second. So in order to find volume, all we have to do is apply the generic definition of volume. Volume is simply the area of that cross-section times the width of it. So on the right-hand side here, this is what we're focusing on. This is where the water exit into the atmosphere, which is where the subscript 1 is. All right. And that we know we can find area simply just pi r square, and then delta x here we don't know, but we can go ahead and get rid of delta x or substitute it out. Well, generically we know that v is equal to delta x divided by time, or distance divided by time. In this case, the problem only flows to the right, so really delta x is the same as distance, and v stays constant for that section of the pipe. Okay, when I say constant, I'm talking about this narrow section, not the y section. All right, so I can go ahead and manipulate this function to find delta x. Well, to get delta x by itself, simply multiply both sides by t. So I can say that the speed at segment 1 times the time of flow is equal to how far it has traveled during that segment. So here I can substitute out delta x for v times delta t. So I'm going to go ahead and do that. So volume 1 is simply the area 1 times v1 times t, but you notice here t does not have a subscript because the time to move a certain mass stays the same. All right, and that, let's go ahead and crack it out. A1 is simply pi r square. Well, pi is just a constant. What's r? R is just half of the diameter. So I noticed in the problem it gives us diameter, not the radius. So please make sure you read. If it gives you diameter, to find radius, just take the diameter divided by 2. Okay. Here, V1 gets carried down, del T gets carried down. So I'm just going to go ahead and do a little plug and chug. Pi, I carry down. R1, well, R1 in the diagram is simply D1 divided by 2. D1 is given as 3 centimeters. So make sure you convert this to meters. So 3 centimeters is 0.03 meters, and then 0.03 divided by 2, because I need the radius. That's what I did here. Okay, so to find the radius, I simply took the diameter in units of meters divided by 2, and I want to square that because to find the area is pi r square, so don't forget the square. Well, v1, the x's speed, according to this diagram, according to the problem here, is 15 meters per second, which is the x's speed v1, which is faster here. And then you notice delta t, I didn't plug in 10. Well, 10 is 10 minutes, but 10 minutes is 600 seconds. Okay, because for every minute there are 60 seconds. So if there's 10 minutes, there are 600 seconds. All right, so I highlight that yellow there. Please just don't plug in 10 because otherwise you'll be goofing. If you do that all on your calculator, you should get a value of about 6.4 meters cubed, because this is meter square, and then times meter, that'll give meters cubed. The unit seconds here will naturally cancel out. All right, so that is our answer for part A. Well, let's do part B. Part B says in the left section of the pipe, what is the speed 2? So what is the entry speed, right? We know the exit speed, so what is V2? Conceptually, when the cross section is wider, I know V2 is slower. And then when the cross section is more narrow, I know V1 is faster, right? They're inversely related here. So I'm just going to go ahead and apply the continuity equation. So the continuity equation essentially says the area of cross-section 1 times the speed at that cross-section must equal to the area of cross-section 2 times the exit speed. So here, A1 and V1 is the exit speed, and then A2 and V2 is the entry speed, just based on this diagram, because the diagram has the velocity arrow, the speed arrow going to the right side of the screen. All right, so keep that in mind. So here, it wants us to find V2, because part B says in the left section, which is where V2 is, what is the speed? So in order to get V2 by itself, I would simply divide both sides by A2. If I do that correctly, well, here's A1. A1 is simply pi r1 square times V1, and then A2 likewise is pi r2 square. And then you notice here the pi in the numerator and pi in the denominator cancels out. So really it just becomes a ratio. Well, what is R1? R1 is 0.015 meters. Once again, the diameter of D1 is given as 3 centimeters. Don't forget to convert this to meters and then divide it by 2 to find the radius. And then the V1 is given as 15 meters per second in the problem. Once again, it says the atmosphere at a speed of V1, which is equal to 15 meters per second. And then R2 is being square. So on the bottom here, well, the diameter on the left side is 5 centimeters. 5 centimeters divided by 2 is 2.5 centimeters. And then 2.5 centimeters converted to meters is 0.025. And I want to square that. And if you plug all this sexy stuff on your calculator, you should get a value of about 5.4 meters per second. So the entry speed of the water here is 5.4. When it exits, though, because it goes through a narrower cross section, it has to pick up speed, which is 15 meters per second. Okay. All right. So keep those in mind. Again, area and speed is inversely related. When the area is large, v is small. When area is small, v is fast. All right. So that is the answer for part B. Part C. It says in the left section of the pipe, what is the gauge pressure? Well, to find the gauge pressure, all we have to do is apply Bernoulli's equation. All right. So to apply Bernoulli's equation correctly for this particular problem, here we have a straight pipe essentially that just has two different cross sections. We have to establish a reference zero or zero reference point. So here I'm just going to draw it to the center of the pipe. That I'm going to call H1. Likewise, on the right side where the pipe is narrow, I'm also going to draw it to the center of the pipe, which is H2. And then as you can see, H1 and H2, if you reference from 0 to the center of the pipe, they're equal distance. So I can go ahead and cross this term out in Bernoulli's function. Why? Because H1 and H2 are equal. So therefore, these two terms are the same. So if they're the same, you might as well just cancel them. All right. So essentially, this function reduces down to just P2. Well, I need to solve for P2 simply subtracting both sides by 1 rho V2 squared. All right. P1 is given, and then the density of water is a constant. And then V1 here is given as 15 meters per second. So really the only thing I don't know is V2. But V2 we already found in previous part B, which is 5.4 meters per second. Okay. So I'm just going to go ahead and plug and chug. Well, what's P1? The atmospheric pressure in units of Pascal is 1.01 times 10 to the 5th Pascal. Well, times 1 half. And then the density of water is a constant. So if you don't know this, you can Google it or hopefully just write this down. The density of water is 1.0 times 10 to the 3rd kilograms per meters cube. Okay. Notice here the unit here is kilograms per meters cube. It could be expressed as different units, but if you convert it, it will all be the same. Minus... V1 here is 15 because it's given, and don't forget to square it, minus 1 half. Once again, the density of water is a constant, and then V2 previously calculated, which is 5.4. Don't forget to square that. So if you crank all this out in your calculator, you should get P2 as 198,920 Pascal. Okay, 198,920 Pascal. Yeah, I'm just gonna leave this here. You could convert it to scientific notation if you want, but I'm too lazy right now. All right. Other than that, to find the gauge pressure that it wants, the function of find gauge pressure is to take the absolute pressure here and then just subtract it from the atmospheric pressure. Okay, so here to get gauge pressure by itself, simply just move this atmospheric pressure to the left side. So this is what I'm going to do. So the absolute pressure minus the pressure at that atmosphere at a certain altitude, that will give you the gauge pressure. Therefore, I can just go ahead and plug it in. Well, I already found the absolute pressure as 198,920 Pascal minus, well, what's the pressure at sea level, right? The pressure at sea level here is just 101,325. And again, sometimes this unit is expressed in kilopascal, but here, because my absolute pressure is in Pascal, I want to go ahead and just use the atmospheric pressure in Pascal. So keep in mind, sometimes it's kilopascal, sometimes it's just Pascal. So make sure you're able to do that conversion factor simply by multiplying 1,000 divided by 1,000 based on whether you want Pascal or kilopascal. And that will equal the gauge pressure here. So if you simplify all that, so if you take the difference here, you'll get 97,595 Pascal. And that is it for the gauge pressure. All right, I hope that helps. Stay nerdy. Don't be whack.